Hello, everybody. This week we're going to be talking about Chapter 10. Chapter 10 is the frequency response of transistor amplifiers. This will be a bit of a review for some of you that remember your AC circuits. There's a lot of high-pass filter, low-pass filter concepts in this chapter. RC, high pass and low pass filters, resistor capacitor, high pass, low pass filters. Now, the resistors are pretty clear. For example, in this common emitter circuit, the resistors are shown here. This bias resistors, collector resistor, and the emitter resistor. The capacitors are coupling capacitors on the output and on the input, and of course this bypass capacitor down here on the emitter, which improves the high frequency response because it shorts it out. C2 in this case, which shorted out in high frequency conditions, which improves the current or increases the current, the collector emitter current in this amplifier. There's lots of formulas in this chapter. So again, you're going to want to take advantage of that equation sheet that I keep touting and encouraging you to create. Write these equations down, use them to do your homework. And do the examples in the textbook, and you'll be in real good shape for the final. I guarantee it. You'll all do very well if you do those three things, okay? In the meantime, we are going to be going over the formulas, and there's a few examples in this presentation here. So as I said, these coupling capacitors are in series with the circuit, so C1 and C3 are coupling capacitors. Anything in parallel is called a shunt or bypass capacitor. So in this case, C2 is a bypass capacitor. All right. The coupling capacitors, so they're in series, that forms a high pass situation, right? Because a series capacitor will short out, any capacitor shorts out to high frequencies, so that basically, quote unquote, improves the connection, the series connection here. So at higher frequencies, you're going to see C1 is going to be a lower impedance, as is C3. At low frequencies, what happens? DC, it's open, so nothing's connected. So the coupling capacitors affect the low frequency response in a negative way, okay? Opposed to C2 here, which is a shunt capacitor, bypass capacitor, that's going to affect the high frequency response in a positive way, okay? See what else we got here. So here is the equivalent circuit for this high pass filter. Rn is the input resistance of this circuit, of this amplifier. And if you remember, what we do is we Theveninize all of the resistors, the R'(E), the AC effective resistance here, and the emitter circuit, and of course the parallel combination of R1 and R2, the bias resistors. Okay, so that's what this Rn is going to be, as we'll see in a minute. C1 is just C1. All right. So this is for the high pass scenario here. High frequency response. And here's the other one, of course, C. And then now C3, its resistor combination is going to be a combination of RC, the collector resistor, and RL, the load resistor over here. Okay? Now, field effect transistors, as you know, have a very high input impedance. They're almost invisible to the load, to the source, as far as a resistive load or impedance load. So all we have is this gate resistor here and C1. So it's simply C1 with RG. That's the filter. Okay, we don't have to worry about anything else. Here's this bypass capacitor, as I was talking about before. The resistors seen by the bypass capacitor include the RE and then the AC emitter resistance and bias resistors and everything. So this is where's formula number one here. You want to put this down. for this particular circuit. And obviously for your equation sheet, you can go ahead and put this circuit on there too. So if you recognize it on the final, you can immediately go to this formula and get the job done. So RE, this resistor, in parallel with R prime E plus R1 in parallel with R2 in parallel with RS. What's R divided by beta? So you have to scale it by beta, right? Because you're reflecting it on through this gain. What is RS? RS is the source resistance. It's not shown on here on this circuit. It's part of the generator in this case, whatever your source resistance is. It's a series resistor right here, right there, okay? You have to take that into account because it's part of the circuit. There's no signal source that has zero output resistance, otherwise it would have infinite energy, which would be nice, but they can be pretty low, all right? It can be in the ohms, but it's never zero, okay? Sometimes we can ignore it. So emitter swamping resistor, right? That's be another resistor right here in between the emitter and REC2 combination. What that does is it lowers the cutoff frequency, all right? It's going to lower it because you're going to increase the effective resistance here. Okay, let's talk about high frequency response. That was sort of low frequency response stuff. High frequency response, it turns out that transistors, both BJTs and FETs, what are they? They're three layers. NPN, all right, or drain gate source, whatever, right? But they're like a sandwich. And that sandwich, the bread and the peanut butter and the other piece of bread, they act like capacitor plates, all right? So as you increase the frequency, the capacitance comes into play. The capacitance between, in this case, the collector and the base, and this the base and emitter, that's CBE and CBC, or CGD, the drain gate, or CGS, the gate source. Those are little capacitors. They're small, they're picofarad, but they do come into play. And that's why transistors, FETs or BJTs, cannot operate at infinite frequencies, right? They poop out at one point in time because these capacitors are there and they short out the whole thing, okay? So, for example, if you run 100 hertz through this transistor, these capacitors aren't going to come into play because they're picofarad. But if you run 100 megahertz or 500 megahertz through these things, these capacitors, even though they're picofarad, they form a substantial reactance, capacitive reactance as a result of that frequency, high frequency, so they do come into play. So that's the high frequency ramifications of transistors. Sometimes we need to deliberately reduce high frequency response, so you can put capacitors around here, external. Okay, here's an important theorem, Miller's theorem. Okay, for inverting amplifiers, we have input capacitance and output capacitance. And that input capacitance is pretty significant. If you increase the gain, let's say your gain's 100, whatever the capacitance is of this circuit, you're going to increase that capacitance by the gain. So if the gain is 100 and you start out with 1 picofarad, you now have 100 picofarad, right? And a little more, AV plus 101 picofarad maybe, okay? So there'll be an example or two on this. AV is the absolute value of the gain. It's not in dBs. We'll talk about dBs in a minute. So the gain is a large effect on the equivalent capacitance. So this is a shunt capacitor to ground, is what it manifests itself as. So 3904 is an example, 3904 inverting amplifier, gain of 25. If CBC is 4 picofarad, CBE is 6 picofarad, you've got CBC times AV plus 1 plus CB Okay, that's what these are, right? CBE is, these are not external capacitors, understand this. This is part of this transistor. We're showing them external, but they're actually inside here. So capacitors in parallel add, so that's why we're adding these, okay? But CBC, okay, gets AV plus 1. So you end up with, these are very small, 6 picofarad and 4 picofarad, but you end up with 110 picofarad. That's a lot from where you started. Okay, we'll change gears here real quickly. The decibel, I think most of you are familiar with decibels already. It's a logarithmic value. It's convenient because you can express large gains and attenuations also with smaller numbers. It's logarithmic, so it compresses everything. Okay, Bode plots, which we'll look at in a minute, are done using this. You studied this in your AC circuits. So these are ratios. Power gain is 10 log of the absolute AP, arithmetic AP, power gain. And voltage gain is 20 log of the absolute value of the voltage gain. Okay, so a little table here. 0 dB is usually 0 dB is usually just a gain of 1. So it's a buffer. So output voltage is the same as input voltage in terms of voltage gain. For power gain, that's very rare that you'll have a power gain that's 0. Usually you would have 0 voltage gain, maybe 0 dB voltage gain, but some substantial power gain. Example of this would be a voltage follower, emitter, common collector amplifier, okay, which we looked at a couple chapters ago, right? They have almost 0 dB or AV gain of 1, but the power gain is substantial. Power gain is basically what your beta is. So you could have a power gain of 100, all right, which turns out to be 20 dB, okay? Here's a nice 20 dB of power gain. Here's a nice little table here, very handy. Notice 1 is 0 dB, okay? Voltage gain is always double because it's 20 instead of 10 log. Minus 3 dB point for power is the half power point. Capacity coupled amplifiers. We'll go back to low frequency response now. The capacitors form a high pass filter. Here's the input coupling capacitor, C1. And what we do here, okay, is we Theveninize all of these. We parallel all of these resistors up, R1, R2, and the input resistance as seen at the base. And we'll look at that in more detail here in a moment. But that's the input circuit, okay? So your 1 over 2 pi RC, we'll see this formula in a moment. You want to put that on your formula sheet because it's used over and over and over again, is going to be, the R in that is going to be this R-in combination. Output RC circuit consists of C3 and RC and RL, okay? And there's the 1 over 2 pi RC on that as well. But you just add the two. Resistor, collector resistor and the load resistor are just added together, multiplied times C3, and then 1 over 2 pi, all of that is the cutoff frequency. That cutoff frequency is a 3 dB down point at which the frequency starts to, the amplitude starts to diminish. Let's say lower cutoff frequency due to C1. Okay, so R prime E is 3.5 ohms and beta is 200. So here it is. RE1 is not bypassed. Why isn't that? It's in series, right? But we're assuming that RE2 is bypassed because we're at a frequency that C2 is shorting it out. That's a pretty big capacitor, 47 microfarad. So it's shorting out RE2 for sure, okay? At this frequency. So R1 in parallel with R2 in parallel with beta, RE1 plus R prime E is this formula here, 2.77K. So 1 over 2 pi RC, 2 pi RC ends up being 57 hertz. Pretty low frequency. So this has got a pretty broadband amplifier down at the low end. Right? Not quite hi-fi, if you will. You'd have to go down below 20 hertz for that. But 57 hertz, pretty good low frequency response. If you wanted to decrease this, bring it down to 20 hertz, what would you have to do? Well, maybe make that 1 microfarad, make that 10 microfarad. What would that do? Well, that would make this maybe 5.7 hertz. That would do it, right? The bypass RC circuit response can be found by observing the charge and discharge path. So here's one path, C2, RE2. Second path is going through RE1 and then through all of the resistors in the front of the circuit, these bias resistors. Source resistance is not shown in this case, again, but that's what RS is. It's a source resistance of VN, wherever VN's coming from. Could be a microphone, could be another amplifier stage, who knows. So here's the equivalent resistance shown at the input. You want to write this on, put this on your formula sheet and use it to do the homeworks and the examples in the text. You might see it again. Critical frequency due to the bypass RC circuit right here. RS is 600 ohms, beta is 200, R prime E is 2.6 ohms. So what we're doing is we're using the formula that was on the last slide in a real example here. So 330 in parallel with 2.5 ohms, 2.6 ohms, and 100 ohms, 79.7 ohms. 1 over 2 pi RC, okay, with this 47 ohm resistor, 47 microfarad capacitor, you end up with 42.5 hertz. Pretty low again. Now the FET circuit, that was a BJT last time. The FET circuit has such a high input impedance that we can ignore the gate resistance entirely. So all we have to worry about is this 0.1 microfarad C1 capacitor and the RG. 1 over 2 pi RC, again, is 1.6 hertz, really low. Here's a Bode plot. You should be familiar with, you should be familiar with Bode plots from your AC circuits. So this shows the low frequency response, showing the roll-off. The roll-off is going to be 20 dB per decade for that one RC filter, right? Remember that? 20 dB per decade. Here's a decade. 0.1 FC to 0.01 FC. We're going down 20 dB. Okay? And of course, the 3 dB down point is where it starts. Perhaps some of you have used the Bode plotter in multisim. You're probably going to want to utilize this in your lab. One of your labs here, do the Bode plotter. It works pretty good. I'm not going to say it's perfect, nothing in multisim is, but it's very handy. It keeps you from having to take individual data points. So you connect the in of the plotter to the input of the circuit, and then the output is any point you want, really, but in this case, it's probably the output of the circuit. And this is what it plots. It's very nice. And you can set the cursor 3 dB below the midband gain. This is midband gain over here. We'll look at that again. And that's your cutoff frequency right there, if you set it to be 3 dB below the midband gain. So apparently this midband gain is 19.462, 3 higher than that, right? Okay, let's look at high frequency response. Transistor's internal capacitance. Remember the sandwich? All these capacitors short everything out. So voltage divider biased common emitter amplifier with a fully bypassed emitter resistor. That means there's no emitter resistor because we're at high frequency and you've got that bypass capacitor down here. The last example was 47 microfarad. That's shorting that resistor out. So this is a wire. So here's your input input capacity, your Miller input capacitance. That's CBE right here. Similar to the example a few slides ago. But let's do a real example here. Source is 600 ohms. Not shown here, but it is there. R prime E 3.5 ohms, beta is 200, CBE is 6 picofarad, CBC is 3.5 picofarad, and the voltage gain is 9.7. So here's our parallel Thevenin resistance, 493 ohms. Total input capacitance is CBE in parallel with the Miller resistance, which is CBC times AV mid plus 1. Great example here. 43 picofarad, when you do 1 over 2 pi RC, you take this 493 ohms, 43 picofarad, and boom, you get 7.4 megahertz. Pretty high frequency. So we were down at in the 50 some odd hertz, all the way up to 7.4 megahertz. Pretty good amplifier from a frequency standpoint. Mid-band gain isn't a lot great. I mean, it's about 10, but still. Okay, for fill effect transistors, similar to BJTs, okay, we have to it inverts the signal because it's similar to the common emitter. This is a common source amplifier. So high frequency model is C and Miller, CGS, right? It's not BE anymore, it's gate source plus the emitter. And what do we got? C and Miller is CGD times AV plus 1. Same formula, only instead of dealing with CB, we're dealing with GD, right? Instead of CBC, we're dealing with CGD. So it's this capacitor in this part of the sandwich, right? Times AV plus 1. C out is CGD times AV plus 1 over AV. That's the formula from a few slides ago. There's homeworks on these and lots of examples in the text, so I wish you would study all of those and do those diligently, and you'll do well in the final, which is coming up pretty soon, right? Next week. So the total frequency response, you take the lower frequency response and the upper frequency response, and you make a giant composite Bode plot. All right, so usually you have 3 cutoff frequencies here, one for the bypass, one for the coupling capacitors, and so on. And then these are the high frequency elements for the 2 cutoffs for the equivalent high frequency capacitors that are in the transistor. And the other one is the bypass capacitor in the emitter. Okay, which would be over here actually. So the bandwidth is between the 2 dominant critical frequencies. All right, so the first one that happens on either side. This area here is the mid-band gain. AV mid is what this is. So this is the gain of the amplifier, AV mid. And you can Bode plot that whole thing. And we had 7.4 megahertz. I don't know what this goes. Yeah, it looks like about 50 megahertz. Yeah. So this is going to be our 47 hertz down here, and that's going to be our 7.4 megahertz, if that's the same circuit, probably is. You could build this and do this in multisim. I encourage you to. Be a good exercise. Now, if you want to put stages of amplifiers together, one of the amplifiers might have a critical frequency, lower critical frequency that's different than the other, in which case you're going to want to use the very first one that kicks in. So it's going to be the highest lower critical frequency is going to be on the left side of the Bodhi plot, if you will. And then the dominant upper frequency is going to be the first one that kicks in on the upper side. So that's going to be the lowest critical frequency for the upper side, okay, if you have multi-stages. After that happens, you know, they add together. Now, if they're all equal, then it's a different scenario, and you have to use these formulas. So FCL prime, which is the composite lower critical frequency, is FCL of both of them, because they're both the same, divided by the square root of 2 to the 1 over n minus 1. N meaning n being the number of stages. So you could 2 stages, you could have 3, 4, it doesn't matter. That number corresponds to the number of stages. So if it's a 2-stage, the n would be 2. Same thing, the upper critical frequency is FCU, square root of 1, 2, then 2 to the 1 minus n minus 1, okay? Okay, couple of key terms. Decibel is a logarithmic measure of the ratio of one power level to another, or one voltage level to another. Mid-range gain, that's between the upper and lower cutoff frequencies. That's the gain that occurs. That's when all of your coupling capacitors are fully engaged. They're at the lowest impedance that they are, but your parallel capacitors, your shunt capacitors, or bypass capacitors, whatever you want to call them, those haven't kicked in yet. So it's the mid-band gain. And critical frequency is when the amplifier filters 3 dB less than mid-range, okay? So that's it for chapter 10. If you have any questions whatsoever, please post them in the discussion section, and we'll handle those as they come along, okay? Thank you.